Everyone, this is C++ modules getting started today. So a short introduction, what this talk is about. So this is meant to be an introductory talk for people who have never used modules before. The goal here is really to help you getting started to try out modules on your own. You will not learn everything that you need to know about modules here. I will omit several things, some of the more advanced features. I will simplify some explanations a little bit in order to focus on what is most useful when you're starting out and trying to pick them up for the first time. My hope is that this will provide a good starting point from which you can then proceed deeper into the topic on your own. In this talk, we are going to focus on the mechanisms that are available in implementations today, which is mainly the named modules part of the specification. We're going to skip over some of the more advanced features or features where the implementations that we have today are still particularly bad at providing support. I submitted this talk because I wanted to provide like a good first talk to watch when you're curious about modules and are wondering how to get started without assuming any prior knowledge on the topic. There are many excellent second talks on modules out there already, and I suggest you watch them because they're quite good. I will give some references in this talk, but you can also find a lot on your own on other conferences. So this is me. You can find me in various places on the web. I'm one of the co-organizers of the Munich C++ user group. We are one of the biggest user groups for C++ in the world in terms of number of members. And we're always looking for speakers that want to visit our groups. We do both virtual and in-person meetings. And we're particularly interested in accommodating first-time speakers since user groups give a really good opportunity to start out if you want to get your feet wet with giving technical talks. So if you're interested in this at all, feel free to contact me or one of my co-organizers. In my day job, I work as a vehicle architect for Woven by Toyota. This is mostly embedded development for automotive systems. So let's dive into modules, and let's actually start out with an example that should be familiar to you all because it doesn't contain any modules. So here we just have the traditional model using header files and CPP source files. We just declare a function in the header file, and then we have the implementation in the source file. And to make this example complete, we're also going to add a client source file, which pulls in the header using an include statement, and then is able to access the function that is implemented there. So this is all very familiar. So let's proceed and take a look how that actually changes when we move on to modules. But before we do that, let's actually think a little bit about what are some of the problems that this model that we have today actually introduces for us. So a thing that is problematic here is that since the preprocessor that is responsible for the includes lives sort of outside the rest of the language, there's very little restrictions to what you can do in the preprocessor. So for example, you can put include statements in very weird places. So maybe you've seen something like this before, where I just have the like part of the definition in the header file, and then I sort of interrupt the definition in the middle and then use an implementation header file to pull in the body of the function. So some people like to do this. It's somewhat questionable, but yeah, people have found use cases for this and like to do this. Of course, this is very easy to mess up and yeah, not very robust in the end. Another problem that we commonly encounter with includes is the fact that we need to protect our header files with include guards, because everything that is defined in the header file will just get copy pasted into the source file. And if we're not careful there, if there are things in there that introduce definitions that are that could trigger the one definition rule, then this could cause an error. So if you're like me, then when you first learned C++, you probably all made this mistake at some point where you forgot the include guard. Then the header gets the same header gets included twice through some path in the same translation unit, and then you get a redefinition error. And when you see this for the first time, you will be very confused. Another problem with header files is that they're not really isolated from the surrounding state of the compilation, right? So since they get just copy pasted by the preprocessor into the place where the include happens, everything that happened before that is still part of the compilation state. So the pathological example here is if I have a class with a private member function, then I would assume that nobody is able to call this, but then somebody who feels particularly evil today might want to define private to public and then has access to that member function, which I considered to be inaccessible. Again, some people think that this is useful. I've seen this being used, for example, for testing, where people wanted to do white box testing and used this as a hack. But it's ultimately not really desirable behavior. Another problem that is somewhat related to this is the fact that the include files don't need to be self-contained. And I mean, a well-behaved include file should be self-contained, but there's no mechanism in the tooling that helps us achieve this. So for example, if we take this example here, where we have a header file that makes use of std vector in the header, but it does not include vector on its own, then if the client looks like this, where it includes vector before it includes this header file, it's going to work. But if I switch around the order of the include statements, then it will start to break, because now it will not know what std vector in a.hpp is referring to. This is probably also an error that you encountered in some form, where like changing the order of includes just mysteriously breaks your build. And tracing this down in a big complex software code base can be quite intimidating. One other problem that we have here is that, so this is a little bit of a different kind of problem. This is not a problem of correctness, but this is a problem of build time performance. If I have like massive amounts of code in the header files, for each translation unit that I compile, this entire code has to be recompiled from scratch, right? And this is one of the main motivators that is often cited for modules, because people would like to improve their build performance, and this here is a major cause of that, right? So if you're working on big projects, you probably all have spent some time just like cleaning up includes, reducing the number of includes necessary to the absolute minimum, because it can have a tremendous impact on build times. With modules, because it is not a textual inclusion mechanism, this is a lot less of an issue. So let's take a look at what modules actually look like in the source code. So this is the equivalent to our example from before. We, again, just have one module that exports a single function. And the first thing that we notice here is this, this module declaration at the top. So our module has to start with such a module declaration to make the compiler aware that it is a module and not a normal C++ source file. And we use the keywords export module here for that. And then we provide a name of the module. And the first thing that might be a little bit surprising here is that the name that we give the module does not need to have any relation to the name of the source file. In a lot of other programming languages that provide modules, this is different, that like the name of the source file has to be the same. In C++, it was decided that we want this additional flexibility here. If we then add the client side again here that now wants to make use of this function, we have to add a matching import statement here, and that will then import the module by the same name that we used in the export declaration above. The module name that we are using here needs to be globally unique throughout the program, and it's the programmer's responsibility to ensure this uniqueness. This is one of the gotchas that you need to watch out for. Like in toy examples, this is not really going to be a problem. But if you think about like how to scale modules, you probably want to come up with a naming convention here that makes name clashes unlikely. I would expect that once like modules get more traction in the community, that we will get like an established convention there that everybody will follow. But for now, it's we don't have that yet, so you just need to take care that you choose your names carefully there. Another thing that is also maybe a bit surprising is you might notice that we just call the function down here by its name. We don't need to mention the module again. It's not put into like some kind of namespace or anything, right? Like I could manually put it in a namespace just like I would have done with the header. But by default, just the fact that it's in the module does not put the name into a different place than it would be in a header file. So one thing that you might notice is that in addition to the export declaration at the top, we also added the export keyword in front of the function declaration. This is another vital property of the modules, that it only makes those names visible to the clients that are explicitly exported. So I can have private parts in the module implementation, and if I don't prefix them with export, the client will not know these names. So what are the things that I can export with this export keyword? So we already saw the exporting functions in the example. I can also export types. I can also export templates, both function templates and class templates. And here, thing to watch out for is the export keyword when I export a template is put in the very front before the template keyword. Like if you're like me, you might be tempted to put it on the second line here after the template type name something, because that's where we usually put all of the various keywords that we accumulate in front of our declarations these days. But with export, it actually goes into the very front. A good intuition here for why that is the right place is that what the export ultimately exports is a name. And the name is introduced by the declaration, right? So what I'm exporting is the full declaration, including the template keyword, right? So it's always export and then follows the full declaration. That's how I remember this. We can also export namespaces. So this is a nice shorthand. If I have a whole bunch of things that I want to export, I can just put them all in a single namespace block, put an export in front of it, and then I don't have to repeat it for every single declaration inside there. Notice that this export is scoped like to the block that it is actually attached to. If I then open the same namespace again and without the export, those additional declarations will not be exported. That's quite important because anybody can open a namespace at any point, right? And if a single export could make all of those declarations mark all of those declarations as exported, sort of like long distance, that would not be nice, right? So it's really only for the one block where you put the keyword that it is in effect. Another thing that you can do is you can export using declarations, and this is particularly useful if you want to export the name from a different namespace than it was declared in originally. This can come in quite handy also when wrapping legacy libraries into a module interface, which we'll talk a lot more about towards the end. Another thing that was newly introduced with modules is these export blocks. So that is similar to like we had it for the namespaces. It's just a shorthand. We have a whole bunch of things that I want to export all at once, and I don't want to keep repeating export all the time. I just put them in such a block. If there's something in this block that does not make sense to be exported, like for example a static function which would have internal linkage, the compiler will complain. So it's something to watch out for, but it's not really dangerous because if you accidentally leave something in there, the compiler will tell you. Finally, you can also export other modules. So here we have one module that exports a function, and now we start another module B, and we want to export everything that was also exported by A under B. And then we use this slightly peculiar export-import combination. So this looks a little bit weird at first. The way to think about this is like you use import to like import something from another module, right? To pull the parts that are exported by A into like your scope. And then putting the export in front of that means I don't just want to import it, I also want to export it to my clients. So that's why you have to repeat it there. And then the client, if they just import B, they can access foo as if it was exported by B in the first place. So the client does not need to be aware that the module A exists. So one thing to keep in mind about the export is that just because something is not exported does not mean that it's entirely inaccessible to the client. So here in this example, we have a module where we have a class that is not exported, but then we have a function that is exported, which returns a value of that class type to the client. And now what the client can do is they can call this function. This is not a problem. They can also catch the return value with the auto keyword, for example. They can reach into the struct and call member functions or get to member variables. All of this works. The only thing that the client cannot do is refer to this class by name, right? So if you try to like use the not exported type name somewhere inside main, you would get an error because that name was not exported. The client does not know about this. And while this might seem a little bit weird at first, it's actually nothing new. So you could already get into similar situations quite easily with the auto return type, where, for example, you can have a type that is locally declared and then return that from your function. And it's exactly the same situation, right? So the name of the type is not known outside of the function, but clients can still use this type. If you are dealing with functions in their code base that return lambda expressions, you might have run into this. That's a typical case where you do this because the type of a lambda is anyway internal to the compiler and cannot be named by the user, so you often use the auto-return type for this. Daniela Engert gave a very nice talk where she goes into much more detail about these things. It's called the 3 secret spices of C++ modules: visibility, reachability, and linkage. And there she explains, like, in great detail what the differences are between those 3 concepts, and gives some examples how they relate to each other. So let's take a look at the different kinds of modules that we can write in the C++20. So the example that we saw so far is what is called a primary module interface. So this always starts with this with the export module keywords, and I can just export functions from that. In contrast to that, we also have the module implementation units, and the key giveaway that differentiates them is that the module implementation does not have the export in front, right? So we just say module and then the module name, but without the export. So the difference between is with the interface unit, I always have one primary interface unit, and that is the one that does all of the exporting. But then I can add an arbitrary number of implementation units who are not able to export things on their own, but they can provide the implementation for the things that were declared in the interface. So this is very much analogous to what we have today with header files and source files, where we put all the declarations in the header file and then hide the implementation away in the module file. We can do this the same thing here. The difference is that, unlike with the header files, there's not a strong incentive to put things into the implementation unless I have some special reasons. So in particular, with the header files, we had the problem that, like, some things, like certain things that would trigger the one definition rule, for example, I just cannot put into the header without breaking the build. That is not the case with the modules. I also don't really have the performance concerns so much. So even if my primary interface gets quite big, that does not necessarily mean that my build performance will decrease considerably. So the 2 reasons why you would that I can see why you would use these implementation units is either if you, like, really want to hide away details from your users, like put them into the implementation files so that they cannot see them. This especially becomes important if you want to ship pre-built libraries. The other reason is if you want to have a fine-grained control when you're doing rebuilds, what the effort is going to be that you need to spend on recompilation. So there, for certain reasons, like, you can isolate changes if you put them into different implementations, and then if you have to make changes to a single implementation without touching the interface, then you only have to recompile that one source file, but you don't have to recompile any of the other source files for that module. You don't have to recompile the primary interface. And because you haven't recompiled the primary interface, you also don't need to recompile any of your clients. So that might be a good mechanism to like, improve your rebuild times if you need to make frequent changes to the module. Then going one step further, you can also split the interface itself into different parts, right? So not just have the separation between interface and implementations, but really split the interface. So here we have a primary module that is called mice, and it exports like two partitions, Pinky and the brain, and those are then implemented in different source files. So here, the module interface partitions also start with the export module keyword, but here the giveaway is that we have a colon in the name. So the module name here is mice, and then the module is implemented in terms of those two partitions. So they have to mention the module name first, and then the colon, and then after that the partition name. All of the interface partitions need to be re-exported by the primary module interface. This is a requirement by the language, and tools are not required to diagnose this if you forget one, although, of course, they will try to. But this is something to watch out for. If you introduce a new interface partition into the code base, you always also must add it to the primary module interface. If you don't do this, it might confuse the build to a point where it doesn't recognize the interface partition correctly, and then might forget to rebuild it when it's required. So one thing here to notice is I declared this type here at the bottom in one of the modules, and this one is not exported. So clients will not be able to see it, but everybody in the module will be able to see it. So even if Pinky wants to create a secret master plan, he will be able to do this. An interesting question that might arise now is, like, nothing is stopping me from also in the Pinky module creating a struct with the same name. So also have a struct secret master plan in there. And in the old C++ world with headers, that would probably very quickly lead to an ODR violation. In this case with modules, the good thing is that the specification actually requires that the tooling is able to diagnose this, right? So one definition rule violations don't need to be diagnosed. If the tool can't figure it out, it's allowed to just continue and produce garbage if things go bad. Here, it's the tools are actually required to detect such duplicate names and warn you. So the thing here is, the way that this works is, if both types are actually the same, then the same as with the one definition rule, it's fine. But if they're not identical, if it's actually different things that reuse the same name, then you will get an error. And you can already see this today if you try it out with Clang. They actually give quite nice diagnostics that exactly tell you like what the differences are between the two types. With MSVC, I think it's still not implemented there. It will just pick one at random, and you might get weird behavior. So those were all of the different types of module sources that you can have. There's one more class of modules, and that's header units. We're not going to talk about header units here today because they have some problems. If you want to know more about them and also why they are problematic, Daniel Russo gave a pretty good talk last year at C++ Now, where he explains in great detail what header units are about, what problems they were supposed to solve, and why they might be a little bit more difficult to implement than people thought at first. His talk has a bit of a pessimistic tone. I think the tooling people since then have become a little bit more optimistic again with regards to how difficult this is to implement. But still, in the tooling that we have available today, the support is not great. So I would not recommend you use header units right now. Also, if you want to know more details about the different types of module source files, Daniela Engert talked about this quite a lot. She has this slide in a lot of her modules talks. This is the latest version from her NDC TechTown talk last year. So yeah, if you want to know all the gory details, check out that talk, and then you will understand all of the subtle differences between these different types. So switching gears a little bit here, let's talk about how we are actually building code with modules, because that tends to be like one of the main difficulties when starting out. And we are going to be covering CMake here, since it's the predominant build system for C++ today, and also one of the few that actually do provide support for modules. So let's start again with an old school example. I'm just using header files and source files here. This is a typical thing that how that could look like in a CMake file. So I do list the headers here, but with most tool chains, that's actually not necessary, right? So this is helpful if you want the IDE to like display the header files properly. But the thing that the compiler really cares about is the include directory down here, right? And then any file that is in that include directory can usually be found with a pound include statement, regardless of whether you listed it above in the sources or not. There's some tool chains that are a bit more picky about there, and a lot of people don't like this behavior, that you could just silently pull in another header file. But yeah, that's how probably most builds work today. So the first change that I want to make to this is I actually want to get rid of this target include directories command, because since version 3.23 in CMake, we have a new feature which is called file sets. And what I can do with that is in my target sources, I leave the source files the same as they were before. But for the header files, I put them in a separate section, which I then prepend with this file set command. And then here in the base directories line, I give the include directory that I would have been passing to the target include directories in the other example. And then I just list all of my header files here. The advantage of this is that I can now give all of the information with a single target sources command. I no longer need the include directories command. And if I also want to add an install step later for packaging this application, then for example, if I want to ship a library package, then including those header files in the package also becomes a lot more convenient. So if your CMake version already allows it, I would recommend you use this mechanism. It's strictly superior to what we had before. So why are we talking about file sets here? Well, since that's also the mechanism that we're using for modules. So module support was introduced in CMake with version 3.28. It, of course, only works with C++20, because that's when modules were introduced. And the way that you specify them in your CMake source file is by putting the module sources in a CXX modules file set. So yeah. It looks very similar to what we did with the headers before. We can also give a base directory. But now what we put here is actually source files. One thing to watch out for when trying this is to make sure that you meet all the prerequisites for the tooling. And that usually means you need to use the absolute latest version of your tools that you can get the hand on. So for CMake, you need at least version 3.28, which was released like about half a year ago. So it's pretty recent. They're still fixing things in there regularly. So make sure you really can get the latest version that you can get your hands on. For Visual Studio, you need at least toolset version 19.34. Notice this is the toolset version. Like when you run the compiler on the command line, that's the version number that you want to look out for. If you just press like the about dialog in the Visual Studio GUI, it gives you a different version number, and that one has no relation. So yeah, that's a bit confusing here with Visual Studio. The CMake support for modules only works with the Visual Studio generator or with the Ninja generator at the moment. It does not work with other generators like Makefiles. So if you're not using Visual Studio, you also need Ninja, and you need at least version 1.11, which I think is the latest version that is out there. With Clang, you need at least version 17. I think officially they had support with version 16, but in version 16 there were so many bugs that it's really not fun. You should make sure that you're at least on 17. If you can, try to go to the trunk. Like the later the version, the better, because this is like there's a constant stream of fixes here, and it really pays off to be at the latest state. With GCC also, currently you need to be on trunk. The module support has been merged into the development branch for GCC 14, but GCC 14 is not out yet. So at the moment, you still need trunk, which means you probably need to build it on your own, unless you can find a nightly build somewhere. Also, even with the latest tools, unfortunately, you probably will run into bugs rather quickly, and you will find inconsistent behavior between compilers. It's not in a state where it's unusable, far from it. Like you can build real applications with it. It also scales quite well, but there's a lot of corners where you have to be careful. If you step into the wrong direction a little bit too far, then it just breaks down completely without warning. So yeah, you need a bit of an adventurous spirit here to try this out. But if you can work within those constraints that the tools set up, it works quite well. So I don't want this to sound discouraging. It's really worth trying out today. A few things to keep in mind when you actually want to start out. So one question that you will probably run into pretty quickly is, when is a source file a module source file, and when is it a regular source file? So in CMake, you have this file set, CXX modules. When do I actually put a source file in there, and when does it go like just with the normal source files in the other section? So your first intuition here might be, yeah, if it uses something related to modules, it's probably a modules source file. And that is not true. And I got bitten by that almost immediately when I tried this out for the first time. So the rule of thumb here should be, if it has an export module in the module declaration, then it's a module source file. If it's a module partition, then it's also a module source file. In all of the other cases, it's a regular source file. So if you're just importing stuff, you're fine, just a normal source file, don't need anything special. Also, if you're in an implementation unit, just a normal source file. If you get this wrong, you will probably get a compiler error. So it's not dangerous to get it wrong or anything, but just, yeah, if you get a compiler error and don't know why, maybe check that you put the sources in the right sections. Another question that arises quite early is, which file extension should I use for my module sources? So when module support was added to the toolchain, a lot of different file extensions started appearing in the different compilers. And in the beginning, this was very fractured, like every compiler chose their own extensions there, and there was a lot of confusion. by now, at least like Visual Studio and Clang have sort of aligned in that they like accept all of those extensions equally. With GCC, it seems that they don't intend to give any special meaning to those extensions. They just leave it to the build system to provide the correct compiler options. I personally would not recommend using an extension. It's not needed if you're using CMake. It can be a bit confusing if you accidentally put an extension in a place where it doesn't belong. And tools can get confused if they don't know about these extensions yet. So in all of the examples that I will show on the slides, I always use the normal .cpp extension. And yeah, so my recommendation would be, if you don't have very strong feelings about this, don't bother, just stick with CPP and you'll be good. If you do decide to use them though, be careful that you only put these new extensions on files that meet the criteria for a module source file from above. Because if you accidentally put them on another file, the compiler might treat them as module sources, even if in CMake you didn't put them in the modules file set, and then again your build might break. So yeah, something to watch out for. So let's take a little time and talk about the build system's role here, because this is one of the major reasons why it took so long for modules to become available. Like compilers added support for them quite early, like both Visual Studio and Clang at least, and also GCC to some extent, had module support for quite a while, but it was not really in a usable state because of the interaction with the build system. And that might be a bit surprising. So let's spend some time to try to understand this better. So why do we need a build system in the first place, right? Like we could just do this, right? We've all done this probably when we started out developing. You can just invoke the compiler from the command line, and that builds the stuff, right? That produces an executable. So the important role of a build system is it tracks dependencies for you. And in the non-modules world, what that meant was mostly keeping track of the relations between the source files and the header files. So if we change any of those headers, we want all of the affected sources to compile, right? The compiler is only invoked on source files, not directly on header files. But if I do change a header, I want to figure out like what is the set of source files that are affected by this change, and then make sure that I recompile all of these. I obviously don't want to miss any source file in this analysis, because if I recompile too little, my program ends up in an inconsistent state. But I also don't want to just recompile everything all the time, because then my build is not as efficient as it could be. So yeah, I really want to find out exactly the set of files which are affected there. In the classical build model, all of these dependencies happen on a per source file basis, right? So each source file has its own dependency tree of all the include files that it pulls in, and they are completely independent from each other, right? So even if two source files happen to include the same header file for this dependency analysis, that is not really relevant, right? This can all be carried out in parallel without exchanging information between the different compilation paths. So how does the build system do this? How does it know what this dependency tree looks like? So the old school answer to this is you tell the build system. So you may have seen makefiles like this. Some projects still use that until today. you can just list out for each object files what are all of the sources that this object file depends on. So both the source files and the header files, I just list them all out. And this works, right? This gives you a valid make file, and it works fine. Of course, the disadvantages here are obvious. If my dependencies change, I need to update this manually. I have to be careful that I accurately reflect the exact structure of the tree. That's easy to get wrong, and it's not really fun to maintain this. So I really want the build system to figure this out, right? Well, I don't want to specify the structure. At most, I want to give a flat list. These are all the source files, these are all the header files, and now you figure out how they're connected. And the way that the build system does this is it asks the compiler for help. So if you invoke GCC, for example, with this -M option, it will write out a dependency file which contains exactly this information. So here, for the source file that were compiled, these are all of the header files that were pulled in as part of the compilation. And then the build system can make use of this information to track the dependencies. So if we think of that now as a processing step in a build pipeline, what happens here is the compiler takes the source file as a direct input, as a command line argument. It pulls in all of the header files according to the include directory parameter and the include statements that it finds in the sources. Then it produces from these inputs an object file as an output, but it also produces this dependency file, which contains the list of all the headers that were pulled in. So usually people don't think too much about this dependency file, since this is something that only goes to the build system, whereas the object file, that's what is actually being passed on to the linker. And if your build system does its job correctly, then you never need to look at this file. Right? But it's there, and it's a vital byproduct for the build process. So what changes now in this model if we switch from header files to modules? So the main change, which we see right away, is that now our dependency tree is no longer just header files, but it is actually source files that need to be compiled on their own. So looking at the compilation step, what happens here, if I compile a module source file, it still produces the dependency file as before, because I still can have includes in modules. But now, in addition to the object file, it also produces what is called a BMI file, a binary module interface. And this BMI file might be needed as input for the compilation of a different source file. So if we look at the this build graph again, where before we had this situation that each source file was compiled completely in isolation with its own build graph and without any relation between them. Now, because of the BMI file, it's all connected, right? Source files can depend on other source files during the compilation, and these dependencies can change dynamically, right? Like if I add an import statement to my source file, I now introduce in the build dependency graph a new dependency to a different source file, and my source file can only be compiled if I already have access to the BMI file that fell out of the compilation of this other source file, right? So whereas before it was all embarrassingly parallel, I can just invoke 1,000 compiler instances on all of my 1,000 source files at the same time. Now I need to respect these dependencies. So similarly, how we saw with the header file examples for the make file, I don't want to have to model these dependencies myself, right? I just want to give a flat list of all of the sources, and the build system should figure this out. If you are willing to maintain these dependencies yourself for the build files, this whole thing becomes a whole lot easier, right? Then you don't need like special support for CMake. You will just have a pretty big pain maintaining these dependencies. But like the standard that we expect from build systems today is that we don't have to worry about this. And that is what actually took so long to arrive. So let's think a little bit about like what actually changes for the build system here. So let's say now some file in this dependency graph changed. What happens now? What does the build system need to do? So we still have the header dependencies, which apply just the same as they did before, right? If my module includes something, I need to include that in the header dependency file, and the compiler needs to figure out, the build system needs to figure out if there was a change to that header file, the corresponding sources need to be recompiled. But what about these interdependencies between the source files down here, right? So that is also something that depends on the contents of the source file, right? If there's an import statement that now pulls in the contents from another source file, that introduces this dependency here. But this is not something that the build system, this is no information that the build system just has by itself. So we do the same trick as we did for the header files. We ask the compiler, right? We run the compiler on the source file and we ask it, hey, what are actually the imports that this source file has that I need to take into account? And the way that this manifests is if you run a modularized build, you will notice that it actually compiles all the source files twice. It does a first pass of all the sources to scan the imports. This is usually a lot faster than a full compilation, but still it's extra work. And then it will start a second compilation path with all of this information included, which then respects the order that are introduced by those dependencies. So this, of course, now sounds like it's not giving us many benefits, right? Because before we had the situation where the entire build was parallelized, we lose that. And now on top of that, we also have to invoke the compiler twice to figure out the dependencies. But it turns out that in the typical code base, this is compensated quite well by the fact that the effort that we have saved by not having to pre-process the sources from the modules that we pull in over and over, so that we get a net positive and quite a substantial one. So of course you can always construct pathological cases where the build becomes completely serialized, and you might actually end up in a situation there where the build performance is not satisfactory. But there are tools for mitigating that, right? Like we saw, you can put stuff into partitions. You can, the same as you did with header files, you can manage the interdependencies between the sources. And like the individual compilation for each of those source files is just going to be much, much faster. And that's where the win comes from in the end. Okay, that's all I want to say about build systems, but I think it's important to also understand this perspective to, get a better understanding for why tools are having such a hard time and why it's taking them so long to support this. So for the remainder of the talk, I want to give you like some useful starting advice that could be helpful if you like just want to start using this and try try to use it outside of toy examples, some of the things to look out for, and yeah, some of the things that helped me when I first started playing around with this. So one thing that you will probably want to do pretty quickly is bring includes back into the picture. So in the ideal world, everything is modularized already, right? So we're importing the standard library here as a module. This is something that was added with to C++ with C++23. And then, yeah, we just use std vector that was provided by this module. We don't have any includes anywhere, and it's all just great. So we're not there yet. You will probably not be able to do this. So yeah, instead of having an import here, you will need to pull in the header at some point. Even if for the standard library you can get a modularized one, you still will have some legacy dependencies where you only have headers. And now you may notice something. Now at the top of our module, I no longer say export, but I just say module semicolon, and I moved the module declaration now down here below the include. So what we did here is we opened up what is called the global module fragment, and that is the place where you put your includes. We will talk a little bit more about the exact effect of that later, but just as a rule of thumb, you don't want to include legacy headers in the module itself. You always want to move that up to the global module fragment. And yeah, this is always the pattern. The includes always go between the module semicolon and the export module, and then the actual guts of the module go down here after the export, and this part is also referred to as the model purview. So global module fragment, that's for the includes. Model purview, that's for like your actual implementation of the module. If you're doing an import, that can go into the module, right? There's no restrictions there. But if you're including legacy headers, they should go into the global module fragment. You need to be a bit careful when mixing headers and modules like this. So, for example, one problem that you might run into pretty quickly is, let's say you're really enthusiastic about C++23. So you're writing a module, it's using the standard library as a module, and now we're exporting a function that makes use of a standard library type. Now my client imports this module, wants to call the function, and now we have the visibility problem here again. Like, it works as long as I use auto, but if I try to use string, then it will complain that it doesn't know the name std string because it was not exported, right? I did not write export import std, I only wrote import std. So everything inside the module will know about all the names in the standard library, but my client will not, right? Because my client just imported m, and m only exports the function f and nothing else. So how do I fix this? Like, if you just now also import std in the client, it will work, but you might be tempted to do something like this, and that will break. And that's a little bit surprising. So the problem here is that when a name is exported from a module, it becomes associated with that module. And if you then declare that same name outside of a module, it's a different name, and the two are not necessarily compatible. And on Clang, for example, we can observe this quite nicely. So let's say I have a function in my source file. If you compile that source to an object file, then you run nm on that object file. That's part of the bin utils, and it will just give you a list of all the symbols that are included in that object file. And then, like, as you probably know, names in C++ are mangled, so they look a bit weird, but you can use the C++ fill tool to demangle the name. And then we see here, okay, this symbol refers to a function that is called the answer. And yeah, return types are not part of the name in C++, since you can't overload based on the return type, right? So this is all the information that the linker puts in the source file. And now if you put that function into a namespace, then the namespace also becomes part of the mangled name, right? So now the function, the mangled function name also includes the name of the namespace here. If we put the function into a module, remember that the module does not introduce a namespace, right? So the function is still declared under its name in the global namespace. But if we look at what is in the object file, we will see that it still mangles it to a different name. So we will have this initializer for the module, which was not there before. But what is more interesting is at the very bottom that now the function name also has this little @myModule attached to this. And this was something that was not there before modules, right? This is something new now. The terminology that is being used here is that the name is attached to the module, right? So if I export a name from a module, that name becomes attached to that module. There was a bit of a debate in the tooling community whether attaching a name to a module should surface in this way, in that it influences the mangling and becomes visible to the linker. The situation today is that we seem to have pretty much universal agreement at this point that this is the behavior that we want. But if you look at the standard, it actually mentions two different kinds of module ownership, is how they call it. This would be the strong ownership model, but there's also the weak ownership model, which would allow for the export not to affect the mangled name. And then the consequence, of course, would be if the same function, like the function with the same name, gets exported by two different modules, the linker has no way of detecting that. And that's, I think, the behavior that MSVC initially implemented. And then the effect was similar to like with an ODR violation. It would just pick one at random, and you wouldn't get a diagnostic. But the way that it looks like now is we're probably going to get rid of the weak ownership model and have everybody use the strong ownership model. Yeah, in that case, the linker can recognize the attachment here and react to it. Currently, the way that it's phrased in the standard, it's still not allowed to have now another the answer in another module and have both be exported. So even though the linker could resolve that, since there's no way to differentiate on that in the name lookup phase, you can't have that. And technically, since we have weak ownership still in the language, tools are not required to be able to diagnose this, but that's likely to change. So the expectation right now is that in the future, if you accidentally mess that up and have name clashes between modules, the tools will be able to tell you. It's just not specified that way. Yeah, but this hopefully makes it clear why mixing includes and imports can be problematic, right? Because like if in one context the name is attached to the module and in the other context it's not, even though on the language name lookup level it's exactly the same name, on the like binary interface level that the build system and the linker see, it's different names. And that's a bit confusing, right? Because it's the same in one world, but it's different in other worlds. And yeah, you have to be a bit careful there. One general guideline here, if you are mixing imports and includes, try to always put the includes first. So if you write a new source file, first do all of the includes, then start with the imports, and don't mix them or change the order. The reason for this is like the tools are working on like techniques for being able to resolve these problems with like having the same name being provided in different contexts. And for the standard library, actually, the requirement is that they should be able to resolve it, right? They don't guarantee that it will work for user code at the moment, but for the standard library, actually, in order to be conforming, it should work. And currently, your best bet is to do it like this. The tools currently are trying to also make it work the other way around, but it's not clear yet whether that will actually work. So for now, the guideline should be, when you have to mix it, try to keep the order like this. And maybe we can get rid of that guideline if the tools manage to solve that problem, but I wouldn't bet on it. Another technique that can be useful is, let's say you have a legacy library, right? It only provides header files, and now you want to modularize this. You probably don't want to rewrite everything that is in this header file. Would be much nicer if you could just say, like, have a single export block, just put the include in there, and then all of the declared names from that header get exported automatically. The problem here is that this header does not only contain the names from that library, but it also contains the names that that library depends on. In this case, it's pulling in the string header because it's using that in the interface. And now if I write it like this, I'm also exporting everything in the string header. And that is probably not going to work. A trick that I can use here is to just, in the module file itself, also include the string header before I include the library header. So what happens here is the string header has an include guard, right? And the include guards are respected during the compilation of the module file, right? The module file compilation works like any other source file compilation, right? So when it sees the first include, it pulls in the string. When it includes the library and reaches the second include of the string now, it will see the include guard and see, oh, I already pulled in that file, so I don't need to do anything. And then you don't get anything from string, you just get the function declaration, right? And now what ends up in your export block is just the declaration of the function f, but nothing from the string header. And this is a pretty powerful trick. So if you're lucky, you can actually front load all of your header unfriendly dependencies in a way here that nothing that is problematic will end up in the export block. And then you can pretty quickly put together module wrappers like this. Felix, a question.
This works if you have clear separation between declaration and definition of the source code.
Yeah.
But what about, for instance, template code, where you want to start getting this modularized?
Yeah.
But not every project is able to consume modules.
Yeah. So templates are a bit more difficult. So in principle, the same trick also works with templates in that it's pulling the template definition out. The problem here is that the instantiation of the template might happen at an inconvenient time. And then what could happen is when it tries to instantiate the template, it actually needs to have access to something from the part that was not exported. So like you imagine that like you have a template that is exported by the standard library, for example, and now you write a template yourself that uses, like, for example, std vector in there. Like with format, that happens a lot because like the formatters are all templated types. And now when that gets instantiated, it happens in the context of the client, but the client does not have access to those names from the standard library that your implementation makes use of, and then it all breaks. So with templates, you have to be a bit careful there. If you're lucky, it's sufficiently isolated that it doesn't leak through. But if you need the name to carry out the instantiation, then it will break. Follow-up question.
Yeah, so then if you have a bigger code base on the then probably the only way is to start hiding the exportability of or the modularization with macros. And what is the alternative? Because
so the proper alternative is to just modularize all the way through. Right, so if you only need to do this trick because I didn't want to modularize string as well, right? If I can modularize string as well and just to import std, then the whole problem goes away, right? The problem only arises when I have to mix the two worlds. So if you can find like a boundary, right, where you can say, okay, here, I keep pulling in this library through includes, but it's an implementation detail, right? I make use of them inside my module implementation, but none of that leaks to my client. That's fine, right? But in the case with templates, sometimes something leaks through to the instantiation phase here, and that boundary breaks down. And then you need to choose one of the worlds, right? Then either you do everything in include land or you do everything in module land. Yeah, yeah. It's there are some techniques also for like making sure that this stuff doesn't leak through, but then that requires, of course, making changes to the library. And if it's a third-party library, you might not be willing to do that. But if you have full control over the source code, you're pretty flexible in what you can do there. Then it's really only limited by how much effort you want to spend in refactoring. Another useful technique here is what we mentioned in the beginning, that we can also export using declarations. This can be particularly useful if I want to export a name into from a different namespace, right? Because remember, we have these two worlds. We have the name lookup world in C++, and then we have the linker world that sees the names that are potentially attached to modules. And I want to make sure that those two worlds are consistent. And here, by exporting a name from the module, right, I now introduced a new name that is attached to the module. And now I have two ways to refer to the class, right? I can refer to it directly the way that it was exported in the header, And when I refer to the type that was exported by the module, I can potentially have a new name for that, right? By, for example, having this using declaration again wrapped in a namespace or something. So this is another technique how to deal with potential conflicts here. Last but not least, a pretty nice trick. So let's say, I want to export a function, right? If I put it in the global module fragment, right? I just either through by pulling it in through an include or by writing the declaration manually there. I can't export it, right? Stuff in the global module fragment cannot be exported. Only in the model purview I can use export. But if I put it in the model purview, it gets attached to the module, and then I might be in this predicament that the names no longer match up. So wouldn't it be nice if I could put stuff into the model purview and export it as part of this module, but without attaching the name to the module? And this is how you do this. You put an extern C++ in there. If you use an extern declaration, I think it also works with extern C, the same, but typically it's C++ functions. There's a special clause in the standard that says these declarations don't get attached to the module. So for legacy tricks, for integrating legacy code, that can be a very useful trick. Another pain point that we have here is macros. Macros don't get, you can't export macros from a module, right? That's a feature. We don't want the preprocessor state to leak to the client. But what if the library that I want to pull in actually depends on macros? Yeah, it won't work. I won't see the macro in the client. The simple solution here is to provide two files. I provide a module file with all of the stuff except the macros, and then I provide a header file for just the macros. That's probably the quickest way out here. Alternatively, you can also think about replacing the macros with some proper language features. Like here, I just wrap the constant into a const exp variable that I then can export. This is, of course, the nicer solution. The downside here is I have to do this manually, so that means some refactoring. And also, I now changed the interface. So also the client code now has to change because the syntax that was used for the macro-based code is most probably not going to compile with this new interface. But yeah, if you have to modularize a library, think a little bit about this, whether it's actually worth doing this or whether you prefer the other approach that is, yeah, that preserves the macros. Daniela gave this keynote at CPPCon in 2022, Contemporary C++ in Action. It's an excellent keynote. She there writes like a fairly complex real-world application with lots of different dependencies and uses modules throughout for everything. So she modularized a lot of third-party libraries, a lot of legacy code, and used a lot of the techniques that we just saw and more to make that work. If you just watch the talk, you probably will miss most of what she's doing, since it's pretty clever tricks and she doesn't talk too much about this. But there's a GitHub repo for this talk, which contains the entire source code for the project. And I highly recommend to check this out because like you can really see the different kinds of libraries. She has a classical C library in there. She has the standard library. She has ACCU in there. So you really have like all the different kinds of libraries that you would encounter in the real world are represented there. And she has a nice catalog of different techniques how to deal with bringing that into the modules world. So how can we deal with external libraries that are built on their own? So what we've discussed so far works well if all of the libraries are still part of the same build, right? I have like a monorepo style build. But what if I want to build libraries on their own and then ship them in binary form to my clients? So that might not seem like a big deal at first, right? So from what we've seen, it seems like the most complicated problems the build system has already taken care of. But maybe you can already think of a few things that could go wrong here. So the most obvious thing is, in addition to like the library object code, I also need to provide the BMIs to my clients, right? Otherwise, they can't consume it as modules. So in the classical world, I just ship like the header files and the object code, like as a static library or as a DLL. But now I also need to get the BMIs there somewhere. The big difference between the code in the BMI and the code in the object code is that the BMIs are consumed by the compiler, right? Remember, if I compile a source file and I do an import, that's the point where the BMI has to be read. And like conceptually, what the BMI contains is, like, you can think of it like a serialized portion of the internal compiler state that is actually written out there, right? All of the information that was obtained when processing the source code from the interface file is included in that BMI in binary form. So this is a much more complicated interface than what the linker sees when consuming the object file. And as a result, this is much less resilient to changes in build options. So if I change compiler flags, even if I only introduce like new preprocessor defines or something, this could already break this. So the current best practice here is to distribute the BMIs in source form. So remember here, I only need to distribute the files that actually produce BMIs. So module implementation files, for example, I don't need to distribute, but the interface files I would need to provide in source form. So if I have confidential parts in there that I don't want to ship to the clients, I would want to split that off into implementation files. A consequence here is also if the BMI file pulls in dependencies through headers, I need to ship those headers as well. You might ask, like, if I ship the BMIs in source file, then why bother shipping modules at all, right? If the client has to compile everything on their own. But keep in mind, the BMIs only need to be compiled once, right? If you consume a library, it's never going to change. On the very first build, it processes the BMIs. After that, it has them in the binary form that it needs them, and then you never need to worry about them again. So it's not a big impact on build times here. So ideally, the build system would figure out any incompatibilities that you could have with the build options and tell you about this and help you out a little bit here. The tooling vendors are working on this right now, but at the moment, it's not there. So like if you look at the CMake documentation, they explicitly say, like, it works fine if everything is part of the same project, but if you use like find package or something to pull in external libraries, all bets are off, right? You have to be careful. Shared libraries are even more tricky. So shared libraries are not part of the ISO C++ standard, right? It has no notion of shared libraries. But there's a few things to keep in mind here. Like there is the additional notion of shared library visibility, which has no relation to the module visibility. And currently, like, you need to manage both. independently of each other. Shared libraries, the major difference besides the visibility between shared libraries and static libraries is that shared libraries are already linked when you consume them as a client, right? So the link process for the shared library happens with one BMI that was produced by the maintainer of the library, and then you ship that to the client, which will consume it in binary form with a BMI that they build on their own as part of their client build. And that has to be consistent. So that's another complication. Right. Yeah, and again, ideally the tools would help out with that, but it's still in an early stage. So you have to be a bit careful if you try to do this. Craig Scott actually wrote a blog post a couple of weeks ago where he discussed some of the implications here for CMake. All right, wrapping up. So modules are slowly maturing, right? You can try them out today. Despite the many pitfalls that are mentioned here, they work, right? And they work quite well for the things that are not affected by these pitfalls. So I would really encourage you, try them out today. Like, be aware of the dark corners. Don't get discouraged if something breaks. But yeah, it's really cool stuff. And in particular, I want to emphasize this last point here. The tooling ecosystem is evolving quite rapidly, and there's a lot of low-hanging fruit right now of unsolved problems and like potentials for new tools that came up now with things in the module world. So if you are the slightest bit interested in contributing to a compiler, to a build system, like deliver some great value here with a comparatively low effort, this is a really good chance. Like, I don't think we will get a chance like this in the C++ ecosystem maybe ever again. So yeah, if you're interested in tooling, in compiler technology, linker technology, check this out. It's great stuff and lots of problems where you can make a difference. Yeah, I included some references to other talks and blog posts. And I also included a little Godbold example to like a minimal hello world with modules where you can start playing around. And that's it. Thank you.